Hey, and welcome back everyone to our little oreboot hackery here. So today we're going to pick up essentially where we left off last time, which was where we already run our code that was written in Rust. And I would like to start with looking at the memory map again of the SoC that we're working on, which is the JH7100 SoC by StarFive. Sorry. SiFive, in turn, made the cores which are being used on that SoC. And if you remember, I was telling you that there is some confusion around what is actually where. So, or what is what rather. There is the SoC, which has the cores, and the SoC is documenting its own memory map, whereas the cores are essentially bringing the basic memory map in a sense. And so I took all the datasheets I could find and drew some pictures. And one of the big questions is, which cores exactly are we actually talking about? So let's actually have a look at that picture here, and I will explain you a bit of what I've drawn here and why. So right here in the middle, this is the memory map that is presented to you in the JH7100 datasheet. Let me zoom in a bit here. Sorry. So this is a bunch of screenshots I put together from the datasheets in my PDF viewer. So here you see this tab open here is belonging to the SoC. So they say this is the memory map of the U74MC. Now, what is U74MC? There is something called U74MC, and on the SiFive website, they're describing that as a complex which has 4 U74 cores, and then there is one more core connecting them. Now, the JH7100, though, only has 2 U74 cores, so something is a bit strange here. Now, on the other hand, there is also U74. So if you look at other places in the datasheets, they only mention U74, not the MC part. And this U74, that's in this tab here from my PDF viewer, that would be essentially one of the 4 cores which are in the core complex. And now if you look at the description of the U74 again, it's actually not saying the cores are U74, but the cores are U7 cores. So it's a bit of a mystery what exactly is a core now or what isn't, and so on. And this is essentially how I ended up with this picture of those 3. And I also looked at the U7 in turn, but that didn't really fit here so that you could still see things, and I will show that in a bit. So, I have drawn some lines here, and those lines are essentially, the commonalities between what's on the left here, in the middle, and on the right. And then I have drawn some peppers. And why do we have those peppers here? Those peppers are where the peripheral part starts. So P for peppers, that is the 2000 quad 0 address here. That's the starting address. So I marked it in, here it's a bit off and also here, but never mind that. That's essentially that. So pepper for peripheral. Anyway, so what are the other red lines here? So essentially, the first line that is common between all of those here. This is the debug port. And if you look closely, I will zoom in a bit because it's probably hard to see otherwise on the video. So this is the just 0000 whatever base address, right? So it says debug, and then there is some reserved space starting from 1000. And of course, this is hex 1000, but I will still read it as if it were decimal. Well, whatever. Now, the ranges here they are still the same. So the debug port definitely, and now the reserve part let's have a look at that. It ends at 1 and then 6 Fs here, 1 and 6 Fs there. Now this here is a bit different again, right? And the question would be why. Part of that is reserved. And so the U74 MC core complex has these extra fancy things here, like an error device and the S7. And the S7 is sort of a glue core, which is sitting on a bus between the U7 cores. And down here you actually see U7, not U74, right? So yeah, they are somehow connected. This is why there are no lines over here. So I will just skip over all of this here, because this is nothing that we have in common. The only thing there is, which sits in between, is the CLint or CLint or clint, whatever you want to call it. It's the core local interrupt. Now, that one starts at 200 quad 0. Do we have that here as well? Yes, 200 quad 0. And then we have the cache controller starting at 201 quad 0. Same again here, ending at the same address. No, it's actually slightly different. Here it's 3 and then 3 Fs. Here it's 1 and then 3 Fs, which might be because on the right hand side here we have more cores. And here again we also have 201, 0 and then 3 Fs, just like here. So I guess that what we have here on the left, the U74, is indeed what we have in the JH7100. Now there's also this thing here, lim. I don't really know what a lim is. I guess it's also related to the cache in a way, because it also starts with L2. So caches are arranged in multiple levels, you know, depending on the respective chip. It can be that there are like, I don't know, maybe 3 levels of cache. You may know this from the CPU or SoC in your laptop or desktop computer. Like AMD, for example, there was news recently that they put some ridiculously large level 3 cache, I guess, in some of their newer chips to gain a lot of speed. Anyway, yeah, lim. Let's actually see what lim is, or if we also have it. So this sits at 800 quad 0, 800 quad 0, ending at 8, 1, then lots of Fs. Here it's a bit different again, so confusion again, right? Do we have the same here? Yes, we do. And here we also end in 8, 1 F and then quad 0. Just like here, actually. So sometimes it matches on the left and sometimes it matches on the right-hand side. No clue why. But if there is somebody from SiFive or StarFive out there, maybe you just ping me and send me a note on that. Anyway, so the JH7100 now, being a SoC, has lots of peripherals in addition. And so yeah, let's just skip over a few things here. The peripherals would start in this range here. The specific details are on the next page, so I didn't take that on the screenshot here because it doesn't really matter. Just wanted to mention it, that there is essentially a gap here. But now the interesting part is there is something called chip link, and chip link seems to be related to the GPIO configuration or multiplexing. So the GPIO pins, you know, they can have different functions. We already talked about this a bit. So if you say I want to use a GPIO pin, you know, you could say it's an input pin, you could say it's an output pin, and just use it as this one single pin. But it could also take a specific function and, let's say, for example, a SPI bus. In a SPI bus, you would have different, you know, pins for specific purposes. And if you already have hardware for it, you know, you don't do things manually, like what we would call bit banging. that would mean that you do very specific operations, essentially just manually by filling up registers. But you would actually have hardware doing that semi-autonomously. So you would still need to configure it and talk to it. But if you already got the pins assigned, then the hardware can pick them up and use them. Anyway, so yeah, we will come back to this chip link thing in a bit. And here you can see there is something called a system port, starting at 4, 3, and then lots of zeros. Yeah, this is essentially this area here. Then there is a few other things reserved. Okay, and now the memory port at 8, lots of zeros, 8, lots of zeros, and the same here, 8, lots of zeros. And this is actually very common. So if you see this base memory address, you will also find that on lots of ARM platforms, for example, and also other RISC-V platforms. Yeah, and here you see also, just like on the right, system port starts at 4, then lots of zeros. And yeah, this is indeed exactly where we have this stuff here. Now this map here is a bit not really in order. So for some reason they decided to shuffle things around a bit. So we have the DRAM at 8, lots of zeros here. If we were to put it in order again, we would actually put it here. And now there is something again, starting with 10 and then lots of zeros. So you see, this is a much higher number, so you cannot address this anymore with a 32-bit register. You would definitely need a 64-bit register. So if you have 8 digits, that's the maximum you could address with 32 bits. So this here is just as they write a copy of the 8 lots of zeros. But they're actually describing that in a reverse order. So at this higher address is actually the primary mapping of the DRAM as it seems. And then it's remapped again to this space. So maybe that is why they put it here first and then this one here later. And in a similar fashion, they have this chip link stuff here. And then again, they would just say, okay, down here, this is the same as before. Now this here is a bit of an erratum. It says it starts at 6100, lots of zeros. And here it says it's the same as 4, lots of zeros. But at 4, lots of zeros, we actually have the VP6. And then at 4, 1, lots of zeros, we have the chip link again. So yeah, this here is off by 100 quad 0, right? So if you just add that to those here, you will get there. Yeah, so this is the fun of reading data sheets. There can always be errata, right? So if you have an error in a data sheet, it's essentially just like if you have an error in the code. Now the problem with data sheets is they rarely get any updates, and usually people need to figure things out and then drop a comment in their code. I've actually seen lots of data sheets which had errata. Sometimes there is like a follow-up post where you have a special extra data sheet saying, okay, these are the errata. Sometimes they also publish an updated version, and then it might be hard to tell the actual difference between the first and the second or whatever revision. Yeah, so as I already said last time, quality differs in that space. And that is true for, well, many occasions, let's say. Anyway, so with all that sort of sorted out, I think we can very much say that we indeed have these U74 cores. Now, for the sake of completeness, let's get out of here and let's look at the PDF I have here for the U7. So here we have yet another memory map, and it also looks very, very similar to everything else. Now, I don't want to dive too deep into this here. I can only tell you that there is one significant difference already, which is definitely telling us this is not exactly what we have in the JH7100, and that's the memory port here. So here it starts at 6 and then lots of zeros, whereas in the other ones we always had 8 and then lots of zeros. So this here is definitely not it. However, there is something called a system port here, which starts at 18 and then lots of zeros, which is exactly where we have in our SoC here. Let's see if we can quickly find that again. Here, this is where we have our internal ROM and also the RAM. So we talked about this when we looked at the boot flow, and we were also trying to read from that address last time. Not getting anything, but that was, as we figured, probably because we were running from SRAM using the, let's say, out-of-band boot flow. So yeah, anyway. Yeah, now you know a bit more about these different cores and the SoC. But yeah, essentially, we don't really have the full clue and understanding of everything here now. At least we're a bit closer. I hope you could follow a bit. At least I'm personally still confused, and I've been looking at this for, let's say, a few good hours now. You know, really just trying to connect the dots here, and I literally did so. So I guess if you were to really understand this, you would need more than just the documentation here, but also the implementation. You know, sometimes documentation diverges from implementation. And then the best thing to look at again is, well, the implementation itself, because it's the source of truth, essentially. That's what you get. So, now putting this here aside again, you may recall I took an outline of the memory map. So this here is my personal nodes. And I now put an asterisk here and another additional entry, because this is where we sort of left off last time. We looked at some of the GPIO configuration, and I was wondering what the addresses were that are written to, or where I could find that stuff in the datasheet. And I think I might have accidentally dropped an 8 here, but let's make sure, because I just copied that from the code that we currently have, which is here. Oh, and indeed, we have the 8 here. So yeah, if you look at this left and right looking very similar, this is a diff between the two Rust files that we also found last time. Let me show you which ones. There is one called IOPad control and one called IOPad. They're almost the same size. When we were grepping for something, we found the same thing, just on slightly different lines, off by 1. Sorry, wrong command. And now, you know, looking at this here, if you just scroll through, you see that indeed they are very, very much the same. And the essential difference is, well, the name, and we have those few additions here. This init thing, and the init has some configurations with a bunch of values. So yeah, we also saw that thing last time, but what we looked at last time was very similar code, just in a different spot. And that was here in the main file of our board. And I was wondering what those were for. So yeah, let's have a quick look at the vendor's implementation of this, because they are doing something very similar. And now let's see if this is something that we recall. So I will just copy this here. Okay. And let's make another pane here. And let's now paste and see what we actually get. So this here is saying set sysconreg register 32, and then it's this value, hex something, C lots of zeros. And if we look at this here, that's exactly the same. So this is now in the IOPad control RS, not the IOPad RS, but the IOPad control RS. And this is exactly the thing which is a bit more on the right-hand side. And now let's look again in the oreboot code. So in the oreboot code, we have those function calls here. So the other part was also oreboot, but this here is the mainboard's code. So here it's setting something in register 89. I want to briefly see if we also find that in the vendor's implementation. So if you recall, this here is the second bootloader, or the first software thing that would be booting from Flash. And indeed, we do find this here, and this is a macro defined in this header file. But it looks like the macro isn't actually called. Now, instead of RG, let's look again with AG, the server searcher. There are lots of search tools nowadays. Yeah, we only get a different color, no different results. Yeah, I actually just did that because sometimes AG and RG, in some regards, they just differ in default. So AG, for example, would also use different casing, whereas RG has some of its own smartness around casing to search for, like, you know, like if you had mixed case, you probably intended to search for mixed case, you know, and stuff like that. Anyway, but those are the quick search tools. Back in the days, people were using grep or grep. Yeah. Anyway, so yeah, indeed that function exists, and I'm not yet sure what it's for. Maybe this header file actually tells us. So let's have a quick look at that. It's line 1201. So let's scroll down there. Well, this is really just the definition of it. Now, if you look at this header file, you can also understand what this code here in oreboot was generated from. So yeah, we looked at that last time. And when we thought, okay, there are lots of functions there, I said it's probably generated. So indeed, it just comes from those header files. So if we expand this here, let's say starting from here, and then jump also to 1201 something. Yeah, it's in a similar range. You see, it's very, very similar in pattern. So yeah, it's always like get and set, and again get and set. So this is for reading and writing a register. And you may also recall that I said, okay, this here looks a bit like super unnecessary. You could just write the value here, like here. And if we look at this here, well, it might be a translation error from the C code to the REST code. But yeah, I want to verify that at some other time. Just wanted to have a brief look at that and, you know, show you that this is where things are coming from. So let's get back to this here. Because this syscontrol main sys thing, this address, I also found that in the datasheet, and let's now see what it's actually related to, or what it means. So we're looking again at the memory map, but we're looking at the peripherals ports, and we are searching for 1185/8000, which we find here. So first of all, I'm at an error. It's not syscontrol main sys. I missed the 8 here. So it's syscontrol IO-pad control. So let's very quickly fix that. Syscontrol IO-pad control, CTL, CTRL, I don't really mind. They put an underscore here. I just put spaces so it's a bit easier to read. That's not what I meant to do. There. Yeah, I'm using the glow tool to print my markdown nicely. It just gives you some colors and, you know, makes tables look like a bit more like tables. So in Markdown, essentially, you can write things as you like, sort of, regarding the indentation in tables. You can try to keep it tidy in this plain ASCII view, but yeah, regardless, Markdown viewer would render it nicely again. Okay, so syscontrol IO-pad control. The problem we had was trying to figure out what exactly this is. So when we search for IO-pad, and we also did this last time, this here is the only occurrence of this. Okay, So now the question is, can we still figure out something more? And for that, I wanted to briefly look at there was another table where we could find all the suppliers of the different subsystems of the SoC. So let's see if we can find something for 1185 something. And let me quickly scroll around and see if I can find that again. There, IP blocks. Their obsession again with intellectual property. Completely bogus and meaningless anyway. So yeah, this 1185 something, that is part of the peripherals. Do we have anything here pointing to that? No, we don't. We only have like chip link, PDM, PWM, but no further explanation. GPIO controller. Okay, great. So yeah, then we are a bit on our own again. And what we're going to do, because we cannot really work with these data sheets in a very meaningful way, we're mostly going to stick with the C implementation now and see what we can take from there. And after a little experiment that I want to do this time, we will get back to looking at the boot flow again and the different components that we have. And then I will show you something that I have in mind, a bit of a design change that is also happening in oreboot now, or let's rather say an alignment with the original goal. So yeah, I already told you a bit about the build setup that we're planning there, which isn't yet fully in place, but we're getting there. And then the vendor here also, they have their own setup, which consisted of a bunch of different stages. And in fact, I promised some people that I would revisit that. I wanted to do that last time already, but yeah, we didn't really have the time. So with those words, the experiment. So last time, we were just booting from DRAM, right? So what we did was we were opening Pico.com to connect to the serial. Then each time I would build a new binary here, and instead of using the full thing, we were just using the boot blob part, and this boot blob part here is then what we were using here. And with my little script, we would just use the JH7100 recover tool, load it to SRAM. This is what -R is for, the recovery binary. That is the argument for something to be loaded to SRAM. And then from SRAM, we would just execute. Now I want to do this. Instead of booting our blob from SRAM, I will write this to the first area in Flash. So this is what we also did with the second loader last time. So what we're going to do now is we're going to replace the second loader with oreboot. And I want to show you a few things first that I might need to change. So last time I commented out a ton of things so that we would just print to the UART. And now I uncommented a few things and iterated over that to find something which would still be able to boot from SRAM. Now I want to see if it also works if I uncomment a bit more and we can just boot from Flash. So yeah, essentially, so there is a few things like the clock setup, for example. So if we don't boot from SRAM, it means the mask ROM wasn't executing the full path that we would otherwise do. It might be that the clocks are not set up, and we actually need to do this here. When we tried this from SRAM, we didn't see any serial output anymore. So it could be that this only works when actually booting from Flash. Yeah, I put a bunch of notes here with fix me. So yeah, let's comment this out now. The next thing would be this here. the UART in it. We also didn't do this last time. And then there is the IO pad control. So there is the on command here that we would still probably need to call. I have no clue actually. So this here is really an experiment, and everything else is just as it was last time. So we were trying to read from different memory regions and then just dumping a few bytes from there, and then we could compare them with what we had and what we expected. So yeah, now this here is only still commented out, and that is also completely okay. So hopefully we will get to seeing this message down here, and otherwise we will still need to figure things out. So now let us copy the run or script and call it run or flash.sh. And let's say we will now start counting at 0. We will say -r recov and then -b boot 0. Okay, that was stupid. Okay, and let's see if that works. Now, one thing I still want to make sure that we don't destroy too much. I want to check if the boot blob that we now are going to write is smaller or at maximum the same size as the second bootloader. So the second bootloader is here in FW, right? It is almost 10K in size, and this here barely 2K. Okay, so we seem to be safe here. Now let's say run or flash. Actually, we're not directly running things, but this is going to happen. I'm going to run the script now. It will wait for the mask ROM to boot up, so I will keep the boot mode button pressed. When entering the mask ROM, the JH7100 tool will talk to the mask ROM and tell it to accept a file for transfer. It will then take the recovery loader, and the recovery loader in turn will ask again for another binary, and that binary will now be our boot blob, and the boot blob will be written to the very first spot in the SPI flash. And then I'm going to hit reset, and we will see if we get to see output. And if we don't, we will iterate. So let's run this, and I will power on the board. Hang on, I need to find the boot mode button. So yeah, there is 2 buttons just side by side. I just need to check the labels again. I also have other boards which may have a different order. So yeah. And that looks good. It's waiting. It's sending the recovery bin. Now at the top, we should, in the next step, see the recovery binary being executed, and then we should see the next file being transferred. Let's see. And there we go. Awaiting confirmation. Firmware update completed. Okay. And now let's see what happens when I hit the reset button. Do we get to see anything? I take that as a no. That is a bit of a shame. So I don't know yet what happened. Now what I would really like to do at some point is to also set up a debugger so that I could attach to the board. There is a bunch of unpopulated pins here, so I could solder a header and then connect one of the debuggers that I have around here, like this beautiful thing here from SiFive, for example. It's quite a tiny board. Yeah, There is also expensive stuff in that space. Unfortunately, that's yet another space where some vendors are trying to make a ton of money without actually providing much of value. So essentially the value is unhiding something that they intentionally were hiding from you beforehand. Okay, now I see one thing I actually missed. So I haven't actually rebuilt the blob, so that would probably explain why we are not seeing anything. So let's actually run make here and build the blob again with the changes that I just did on the left-hand side. And then let's see if we're a bit luckier this time. So we're flashing again, and hopefully that will work. So yeah, sorry. Things like that happen all the time. No. And if that doesn't work, yeah, I'm actually out of ideas for the time being. And that is mainly because, even after reading through the data sheets a lot, I still couldn't make much sense of that. And yeah, then we will just get back to reading the code. We could also at some point look a bit at the mask ROM and see if we actually find a switch there which is saying like, okay, if you press the boot mode button, we're going to execute this now, and otherwise we just jump to somewhere else. So I hit reset, and once again we don't see anything. Yeah, that's a shame. So yeah, I just hit reset again, keeping the boot mode button pressed so that we would see the copyright SiFive line. So now the last thing we could do is we could run the run script again and see that we get back to a working state using the recovery bootloader and the second bootloader again that we already modified at some point to say bootloader. Oh, hey DRAM forever. Try the other UART port 4. I mean UART number 4. Yes, so UART 4, yeah, starting to count at 0. So it would actually be UART 3. And UART 3 is the one I'm connected to here. So everything that you see here on the right-hand side, all the output is coming from UART 3. If you set IO function cell to 6, the UART 3 port goes to the 40-pin RPI headers, the GPIO headers, which are like, yeah. So yeah, that's a good point, but I'm not exactly sure why I would want to do that, because that means I would just need to move my cables to the other port again, or to the other header. So I already have them connected to that one header. So why would I want to remap that to the other header? And, so yeah, I'm not sure I'm following what the idea is. Yeah, so let's recover first now. So this is again transferring the recovery boot and then reflashing second boot. So yeah, about the IO function cell or select, let's actually see where we find that. So I'm copying that from the chat now. Do we find this somewhere here? No, we don't. So I guess that is something you found in the datasheet. If you read the datasheet about the function 1 through 6 listings, you'd see that it just does that for some reason. Okay. Yeah, sometimes those datasheets can be very surprising. So we don't find that here. Do we find function? No, we don't. So do we find anything? So page 62. I guess you mean not this numbering, but the other numbering. So this is off by 10. Are we talking about the chip-link table here? Yeah, right. So, yeah, right. This is also what I recall seeing. Yeah, I wanted to talk about this chip-link stuff here at some point anyway. Yeah, so pad func share, you were saying func share cell? Well, which pad would I need to look at? So function 1 through 6 listings, those ones here. Do I want to look for UART in this table here? It's very hard to navigate, to be honest. I mean, if you search for something, you can probably find it by just typing what you're searching for. Oh, okay, so here we have UART 0. We're looking for, oh, look, this is UART 3. Okay, so UART 3 is GPIO 13 and 14. And the default function would be this here. Is that the default function? Hang on. Oh, wow. No, this here is. So, okay. So this here is the default function, right? The first column. So the first column is the one which is saying UART, right? Okay, so this here is the default function. And you're saying function 13 and 14. And so func share is related to the GPIO pin in a way. Let's see, 13 and 14. Okay, here we have func share, 13, 14. Here we have GPIO. How the heck does this work? Okay, I would also need to look at the schematics. I see. So what is the difference anyway between chip-link and GPIO and whatever else we have here? So here we are referring to GPIO something, and also here. So I guess this is just the name of the output pin, and you can just route some functionality from here to that output pin or something else. Pad func share are what they call GPIO when they talk about the Raspberry Pi header. So yeah, the 40-pin header. Okay, it's sort of starting to make sense in a way. I'm just a bit confused that we find things twice, like in this column here, where it says GPIO something, and then again here, where it also says GPIO something. I find that very confusing. So is it like what is in GPIO here is just redundant and just a different order than everything else? It wouldn't actually make sense to me because the first column here is always the default function. Huh. Okay, so pad func share 13 is GPIO 13 on the header. Okay, let's do the following. Let's really quickly verify that we are back recovered. So I will just hit reset here, and then I hope to see something above here. No, I don't. Oh, okay, now I'm following. Okay, so let me just grab a second UART adapter. So I think I'm confusing myself also all the time with these headers. Let me quickly attach this here. So when we boot from Flash, we need to look at this other header, essentially. And I was looking at the wrong UART. Oh, wow. So I'm turning that on. And so this is so confusing. Now I will say minicom TTY USB 1. I will hit reset. And when I hit reset, I expect to see something here. But I don't. Why do I not see anything? Huh. I thought we would be recovered and this would now be the same binary that we already had, and that was definitely working. Did I just swap RX and TX again? Maybe. Let me just make sure. Hang on. Yeah, I actually did, I think, because it's so I have a different header which has a different order. Oh well. I will actually turn off the board because you can never be sure which things you may accidentally touch. I already destroyed a board by accident by, just touching something. Okay. You can really never have enough of those here. All right, so first I'm turning on the second USB UART thing again, picocom. So when I go to the mask mode, I should see something. I should see something. Oh, yeah, sorry. I need to supply power, of course. Okay, I do see something. Now the other one. Now when I reset, I should also see something on the left. And I do. Okay, good. And now I will run the script again to flash oreboot, and then we will see if we get some output from oreboot. Yeah, the baud rate is correct. It's 119 to 100, 115 to 100 here. I mean, we could see something, so this is all good. Yeah, thank you so much for helping me out here. It's really confusing with these headers. There are like 3 different things called GPIO here for some reason. Oh yeah, I guess just go on with the stream first. Oops. Yeah, sorry. No, all good, all good. Yeah. So, I guess you could just resolve the confusion. I expect now when I hit reset that we see something from oreboot, and do we? Oh, well, that's very unfortunate. We don't. But I also know why. So, confusing again. So oreboot was actually using the recovery UART, and it would turn it to 115/200 baud. So, oh dear. So I will pick this up again, 115/200. So this is again on the debug UART. I will reset that. Huh, well, still nothing. At least we tried. Yeah. So let's actually see if I missed something here, or if there was something I still commented out because I wasn't really sure. Starting at the bottom. So It might be that this here is essential, but I'm not too sure. This was already commented out before I started, I think. No, I actually changed this line here. So maybe we do need this. But it says cannot find value in the scope. So yeah, it's not even imported. Then let's forget that. Maybe I just changed the indentation there or something. Could be. Okay. So what else do we have? Yeah, we have this here. Syscon. But I think we have a second syscon somewhere, don't we? Let's see. Syscon. Yeah, we have that one. And we have this one. And do we need this first? I don't think so. So this here was also already commented out earlier before I got started here. We can see it in Git again. Yeah, this is the wrong spot. Sorry, I don't know why I jumped down. Anyway, you can see this is unmodified here. Also, the spot where the UART is initialized is also unchanged. I only put this comment here in a different spot, so it was further down. Are you using two different tools for the serial comms? Yes, I am. So I'm using two different USB serial converters, and I'm also using two different software tools. The one that you see here on the right, this here is PicoCom, and I'm doing that because it allows for concurrent access to the device. That wouldn't work with Minicom here. Otherwise, I mostly just use Minicom because I'm used to it. Yeah, but I'm doing that because we need to talk to the same UART down here when we're talking to the maskROM, and we send a file to the maskROM, you know, for being executed. Yeah, and here down on the left, it's now hidden. That would be Minicom, and Minicom would show what is happening on the second UART. Okay, so since this is now once again a big puzzle, and I want to get at least something out again today, I want to now have a look at something that I already started in oreboot, which is explaining the boot flow, and so that we have a comparison. I also wanted to look at the vendor's boot flow again. I think that was here in this document, or maybe it wasn't, then it was the other one. Yeah, this one here, the boot user guide. Yeah, this one. So this here says boot flow, but it's a slight little bit more on a high level. So this flow here is essentially something in hardware. This is what we cannot change. And then it branches off after entering the boot ROM. So the boot ROM would either enter a bootloader. So this here is the special boot mode, which lets me talk to the maskROM or boot ROM. And this here would be for booting from flash. And this bootloader here would be the one that we are writing. That would be oreboot, or it would be the vendor's second boot. And besides the second boot, also whatever else they have, which we will look at in a bit also. And then they would continue with whatever else. It says OpenSBI U-boot. U-boot is actually also a bootloader. OpenSBI is setting up a bunch of handlers and drops into a different mode, so from machine to the supervisor mode. But essentially, it's also a bootloader again, because again, it's loading something and executing it. Yeah. So yeah, it's like we have, I don't know, 6 bootloaders in a chain here. Now, where's the other graph? Didn't we have something? Was it here maybe? So this here is the recovery instructions, if I recall correctly. And I thought we had some outline of the boot flow here as well. Yeah, nah, it doesn't really look like it. It only has the instruction to build the different parts. Well, I guess that leaves us to drawing something. And using this here as a base reference for guidance. So yeah, but first let me open something that I already filed a pull request for in oreboot. Hang on a second. So I've already drawn a few images there, which are, one of them is called Matroshka. If you don't know Matroshka, it's a Russian thing. It's these dolls that you can stack, you know. You have one small doll and then you put another doll on top around that and then another one. That's why I'm calling it Matroshka. This is now the exported PNG. Oh, there is also an SVG. Could look a bit nicer. Let's see. Yeah, but then we're missing the images. Yeah, thank you whoever is working on this stuff here. Anyway, so let's look at this slightly blurry image now. It's meant for being inside the documentation somewhere. Maybe I will make a larger export. But yeah, first of all, let's talk about what we see here and what the idea would be. So this is what we have in mind for having in oreboot. So this is essentially the image that we would write to a flash part. So commonly on mainboards, we would have a so-called NOR flash on the SPI bus. So the SPI bus, or serial peripheral interface bus, is used for accessing those storage parts. They are very robust and so on, so that's why they are very suitable for storing firmware. Vendors sometimes also go for other forms of storage, but this here is like what you will very commonly find also on laptops and so on. Anyway, so we would start executing our code, and that always depends a bit on the platform, how exactly it works. On the VisionFive here with the JH7100 SoC, we are mapped to memory when our code is being executed from flash. And in this case, we would do what is called zip, or execute in place, XIP. And that means the memory map, which now just really reflects what is written on the ROM, you know, it can be just addressed and executed. So it's just like if you had something somewhere else in memory and, you know, you were just executing what is there. And in the very first stage, we wouldn't want to do much. We just do the initialization of, you know, clocks and whatever else is specific to the platform, the DRAM controller. And as soon as we have DRAM configured, we head on to the next stage. And now we need to load the next stage to memory first. So we now need to read all of this here from the SPI flash and put it somewhere in memory in a suitable place. And so I put this all in orange, but this will not be a contiguous thing in memory. So we will write oreboot to where DRAM starts. So that would be 8 lots of zeros on the JH7100. And then we put our payload, which by convention we're using a Linux kernel for, you know, with a small environment. We would load that to an address that Linux is actually made for, and that would be the address 8020 and then lots of zeros. And inside of Linux, this environment here, this is now where we have something which is similar to U-boot proper, as it is called, where you have a small like shell with commands that you can run, or we can also put something graphical in there, or a network service like the CPU daemon, for example, so that we can instrument the platform from outside, or just import it as resources and not even consider booting any further because we already have it up and running, and that might be all we would need in that scenario. So now let's actually see, sorry for the coloring, let's actually see what we have here in the manual. So this would look very similar. Sorry. So this part here, which is called oreboot ROM, would be very much what is called bootloader over here. And then where we have OpenSBI, this would be the RAM stage here in oreboot, or we just want to call it the payloader stage nowadays, because its sole purpose is really just to, read the payload, put that, in place, maybe decompress, and then just execute it. So yeah, again, it's not much to do there. It's just that because we're on the RISC-V platform, on the specific platform, there might be something you might need, and we would want to run Linux in S mode. So we also use an implementation of SBI here. And instead of OpenSBI, we would just use Rust SBI, because we can simply pull it in as a library and then, do a function call here. And then just keep executing with Linux here. So yeah. Here, they're saying loading Linux, that could be from whatever UART. I wouldn't suggest that because it's way too slow. Ethernet, SPI, SDIO, USB, you name it. But our Linux kernel here would already come from Flash. And then if you wanted to load another kernel, you could do that again from here, right? So you would have all the rich drivers for, really all the storages that you could imagine, which it could include something on a PCIe bus like PCI Express, or I don't know, SATA, or whatever you might find on the platform. So, oh, there is a question here. What can I read up more on the basics of the project? I don't want to destroy the stream with too many questions. Oh, no worries, actually. That's what we're here for. So the purpose of the stream is really to make the project here public, and actually allow for asking exactly those questions, because as you can see here, so this is from an open pull request, actually. We're still in the process of, setting some things up. So yeah, every question, every remark is always very, very welcome and helpful here. Yeah, should we draw something? I think it's not such a bad idea. So yeah, I will just move things around a bit. So I will now move this here, start to end. I guess we don't need start. It starts with power on. I will put that here. I will put this here. And then I will start a little sketch and show you what the vendor code does. And for that, I'm going to use draw.io, which is also what I use for creating this other diagram. Here you see it's a previous version of that. Yeah, let's discard that. Oh, and there is other things I did. Anyway, so we're starting off with a blank diagram. And now we're going to draw a few boxes here. So yeah, this will be a rough sketch, so I won't spend too much time on this. So box number 1 here gets a label, and the label is second boot. And so that you can read it better, I will just increase the text size and make it bold. Yeah, I think that will be sufficient. We can zoom in again at a later point. So this would be second boot. Now the next part in the vendor code is the DDR init. After DDR init, at least this is how I understand it, comes the first part of U-boot, which is commonly referred to as U-boot SPL for secondary program loader. After that, we would have OpenSBI, and after that, we would have U-boot proper. Well, now we can draw a lot of arrows here, so from here to there, from here to there, and again, and again, and well, this is where we would start from the mask room. So let's make another arrow, which is just entering here, and it comes out of nowhere. Yeah, whatever. Thank you. So now let's hold this all side by side. Like this here. So we see the idea overall is always still the same, right? So you go from one stage to another, and you would always do one step and another one, you know, gradually building up the flow. And so if we look at this here, second boot and DDR init, we will replace those two with just one thing in oreboot. So this would be what oreboot ROM is for. And now what happens in oreboot RAM is the same as those two here. And then the payload in oreboot would be the same as this here. So essentially we're taking away some of the complexity. So I looked at the vendor's implementation a bit, and I could see that they were always implementing reading from a SPI flash. But I didn't really understand that, because technically we should be memory mapped on the JH7100. So we could also just, you know, continue executing in memory and just do a jump. You know, or just copy something to DRAM and then jump to there. But we could still just copy from memory to memory instead of, you know, doing this whole dance. Why do you have so many bootloaders? Technically, you could have a single one doing all of that work. That is a very, very good question. And this is what I want to look at the second picture again for. So essentially, you will always need at least two stages. And the reason is because when you power on the platform, you do not yet have DRAM. And in the first step, you will only have very, very limited space. That's the SRAM. So SRAM is, you know, just like some kilobytes of memory. Sometimes it's like 32 kilobytes or something. And in this stage, because you do not yet have DRAM, you need to initialize DRAM. Now, once you have DRAM initialized, you can put something in DRAM and execute it. And so technically, you could now implement lots of drivers for all the peripherals that you may want, including SATA, including network, whatever, to load a full system and put that thing in DRAM. Now the problem is the SRAM is not really sufficient for doing that. And well, if you even try to squeeze things down, now the problem is you would essentially be implementing lots of drivers which already exist in other projects. So for example, in the Linux kernel, you know, we have tons of drivers for everything. And that's why we, you know, instead of putting everything in oreboot, we just use the Linux kernel for having all of those drivers. Yeah, right. So yeah, if we wanted to have everything together, we would need a huge SRAM block essentially. Yep. Yeah, I guess that wouldn't ever work because SRAM is also very expensive to produce. And so, yeah, nobody does that. I mean, if you buy parts, you know, of course, DRAM isn't super cheap, but at least it's a ton cheaper to produce than the SRAM parts. So the SRAM parts, they are integrated in the package of the SoC. So there is not much space there anyway, unless you want to expand your SoC to this sort of size. There are some SoCs which also have DRAM integrated, fair enough. So there you don't need too much of a setup, but usually that's not even much. So in some cases it's like 64 megabytes or something. However, I also talked briefly about AMD earlier, and AMD did this thing at some point, and just actually did create a very huge SRAM, or cache actually, which is essentially like SRAM, so it's also much, much faster. So on that platform, technically you could do everything there in the cache. Yeah, but then you might need to fight with the mechanisms which are special for the cache there. Yeah, this is like the most portable approach here. You can map this to basically every platform that you can find, I think. Okay, makes sense also from a software perspective with code reuse, single responsibility, etc. Yeah, exactly. Yeah, but thank you very much for the question. I think it's always good to recap those things. When people have been doing this for years, they might take things for granted. And if somebody enters the project, they have no idea, like, why is this so complicated? Yeah. It also actually took me quite a while to figure this out. And, I also started to understand that not every platform is really the same. And it's hard to find, some commonality, which is really true for everything. But at least this SRAM DRAM thing is, you find this for, let's say, every application processor. If you look at microcontrollers, usually they don't have DRAM, and that's mostly what distinguishes them. So somehow they are converging these days. But one major difference has always been that an application processor would actually have a memory management unit. And so you could use something like virtual memory and, make use of a hell lot of DRAM. Yeah, but there are also microcontrollers nowadays which have some hundreds of kilobytes of memory. And that could even be enough for running some very tiny operating systems. Like, there is a Plan 9 derivative, for example, which is called Inferno. That could technically, if you squeeze it down, also run on some of the ESP32 microcontrollers. Anyway, yeah, I hope I could explain this here a bit more. It's a bit of a shame that I couldn't really find the other flow that I thought I would recall, because we also looked at that in a previous stream. Maybe it is here in the document and I just skipped it, but I don't think so. Or maybe it was just described somewhere else. Yeah. Oh. Could be here actually. So we have lots of PDFs, confusing you a bit. And I think I found it again. Right, here. So yeah, the thing I've just drawn is exactly this here. So if we put it side by side again, you will recognize this, right? So we have second boot, we have DDR in it. They do not have U-boot SPL here, but I'm very sure it will be between DDR init and OpenSBI. It could also be that they actually do skip it and this here is not applicable. So yeah, if not, then yeah, just ignore this part. But anyway, it's continuing with OpenSBI and U-boot. Yeah. Anyway, but yeah, what you were saying there, Ralph the Ninja, by the way, for people not in the recording, or Ralph the Ninja 1. Yeah, what is definitely not necessary is having this here in two components. So currently, when we use the recovery bootloader, we are writing those separately anyway, and this here is really just loading this here again. It doesn't really make sense. And also, this conglomerate here, yeah, it could also live in the same space, but yeah, that's not how OpenSBI is designed. So OpenSBI is also designed for reuse in a way. But yeah, the way it's working in C is not like in Rust, where we can just load a crate from somewhere and call a function. You would have these header files gluing things together, and yeah, so it works a bit different. There's no uboot SPL on the VisionFive. Okay, yeah, that's good to know. So then let's really cross this out here. Goodbye. And then we can actually move this down. Okay. So yeah, this is then the actual flow, like this. Okay. So second boot EDR init OpenSBI uboot proper. Yeah. So yeah, regardless of how you put it, yeah, we somehow always end up with a bunch of components. It's a bit weird, but yeah, that's what you get in terms of trade-offs, right? Okay, so we were not successful with seeing something from oreboot today, which I will see if I can figure this out again. I will take DRAM Forever's comments on the fancy GPIO and funcshare and so on. Can I paste that here? I just copied this. Yeah, excellent. So this here is the chat. I just copied that from the recording tool. So I'm using OBS Studio. It's really a great tool. If anybody ever wants to do video recordings, use OBS Studio. There is no better program on earth. So yeah, now you also have a full copy of the entire chat. Yeah, so this thing here is what I will need to look up, and I will also need to look at the schematics. I think I actually have them here in the hardware directory. So that would be this one. Yeah. But yeah, I will need a while to dive through this because, yeah, navigating those also takes a bit of time usually. At least they were nice and put some labels here. PMIC. That's also what I mentioned at some point. It's probably power management IC. And it also looks like it because lots of power rails are here, or at least a bunch of them. Interesting. Yeah, this is all the power lanes. It says VIC power, so we figured that they sometimes call the SoC VIC, whatever that means. So IC could be like integrated circuit, and I don't know what V would be for. Maybe for VisionFive, I don't know. The DDR controller, GPIOs. And here we have funcshare 13. Funcshare 13 x2. That was the thing you mentioned earlier, right? So if we look at this, no, this here again, there, func share 13. 13 is also GPIO 13, so x2c tx data 10. Yeah, that matches here. Okay. And the K7 is probably the coordinate of the ball on the ball grid. And there is a 21 here, 17, 18, 19. Whatever those are for. Huh. Okay. Yeah, I will have a closer look at that and get back to that on another stream. So yeah, for next week, I will see that I can figure something out so that we eventually do get output from oreboot, unlike earlier. So that we get something on this side here, just like with the vendor's code. So yeah, when I power this on again, we don't see anything. I will recover this here very quickly and yeah, re-verify that we indeed still get something using the vendor stuff. And then I hope we can get along a bit. If that doesn't work either, yeah, we might need to read through a lot of data sheets or, well, actually the code. So as I said earlier, if the data sheets are not too helpful, we can just look at the documentation, which is the code. Yeah, and with that, I say thank you very much for today. And I guess I will see you next time again for another stream. Take care.